Welcome to the wonderful world of minerals. Got lots of cool mineral samples to show you, and we're going to be looking at lots of different things related to how minerals form and how we can identify them. Let's start by looking at our Unit 5A learning outcomes. Go ahead and pause the video and write these down. Lots of people confuse minerals and rocks. Rocks are made of minerals. So for example, there's a rock at the top here called a granite. And you can see that the granite has lots of different colors in it, and those are individual minerals. So everything in here that's kind of a glassy color is the mineral called quartz. The dark colored minerals are minerals called hornblende. And then the pinkish or salmon color minerals are called feldspar. So we're going to start by learning about minerals, and then eventually we'll be looking at rocks. I'm going to present some information that will give you the background for the next video you're going to watch in terms of the structure of minerals. So minerals basically are made from elements, and an atom is the smallest piece of an element that still retains the characteristics of the element. For example, an atom of gold still has the melting point of gold and the density of gold and all the properties that gold has. If we get to smaller things than an atom, then we're talking about subatomic particles, and we're not going to go there for minerals. So the elements are all put together on a periodic table called the periodic table of elements. Now this one is taken from your textbook, so it should look familiar if you've been reading along in your textbook. For those of you who aren't familiar with the periodic table, I'm going to give you a quick overview. Each element on this table has its own unique number, and you read the elements from left to right, top to bottom, just like you would read a page. Element 1 is hydrogen, and it's in the top left. Element 2 is actually over here in the top right. Then we come back here to element 3, which is lithium, 4, which is beryllium, and then we have another big gap, 5, 6, 7, 8, 9, 10, etc. So every element has a unique number, and that number represents the number of protons in the atom. For example, carbon, which is right here, is element 6. That means atoms of carbon have 6 protons. If I take a carbon atom and somehow I manage to squeeze another proton in there so that there are 7, then I have nitrogen. I no longer have carbon. So the number of protons dictates what element it is. Each element has an abbreviation of 1 or 2 letters, and I'm not going to expect you to memorize anything from this. You'll always have this table available to you. The rows are arranged such that there are similar characteristics in each row. And the columns also are families that have similar characteristics. These are something you might learn in a chemistry class, but we don't really need to go into those details. One thing I will show you are these weird rows down here. This column here, column 3, as I said, all the elements have some similar properties. Well, it turns out that elements 57 to 71 all share properties of column 3 and this row. So really they should all be stuck right in there. So this is almost like a little footnote down here telling you these all belong up here. Similarly, elements 89 to 103 belong in this little space right here. But the table would be really awkward if we stuck them in there. So that's what that means. There are 92 naturally occurring elements, and element 92 is uranium. The rest of these are made in the lab and are very short-lived. So if I asked you how many protons are in calcium, would you be able to answer that? Well, here's calcium over here, Ca. It's element number 20, so it has 20 protons. If I have a calcium atom that's neutral, then I actually have the same number of electrons in that calcium atom as well. So a neutral atom of calcium has 20 protons and 20 electrons. Protons have a positive charge, electrons have a negative charge, and so if you have 20 of each, they balance each other out and you have a neutral atom. Neutral means it has no charge. So let's talk a little bit more about atoms in general. All atoms have a central region called a nucleus, and inside the nucleus are the protons, which I just mentioned, and they have a positive charge, and then another particle called a neutron, which doesn't have any charge, but it does have mass. We're not really going to talk about neutrons when it comes to mineral structure. Then around the nucleus are the electrons, and these are negatively charged particles. And there's a couple different ways you can think of how the electrons are arranged around the nucleus. This is not really how we think that electrons are arranged. This makes it look like they're like planets going around the sun or something. But for our purposes, this will work. So remember, positive and neutral particles are in the middle, and then negative are out here. Negative electrons are out here. Now, there's some rules I want to mention in terms of where electrons can go. So I'm going to call each of these circles here a shell. Okay? And the inner shell of any atom can only hold 2 electrons. That's what these little spheres are, electrons. Once there are 2 electrons in this shell, it's full, and the electrons have to go to the next shell. The next shell can hold 8 electrons, and the following shell can also hold 8 electrons. When any given shell is complete with electrons, it's very stable. When atoms combine, they form compounds, and there are 2 ways that atoms combine, or bond. One type of bond is a covalent bond, and this involves electron sharing between 2 atoms. Another kind is an ionic bond, and this is an electron transfer between 2 atoms. So let's look at each of these. Electron sharing between atoms forms very strong bonds. Examples include carbon in diamonds and silicate tetrahedra, which we're going to learn about as we learn about the main group of minerals, the silicate minerals. Remember that we said carbon had 6 protons. The chemical formula for diamond is just carbon. Each atom combines with 4 other carbon atoms to form these very strong covalent bonds. This shape right here is called a tetrahedra. If we look at this in a slightly different way, here's the nucleus of the carbon atom. Here are 2 electrons in the first shell, and then it has 4 electrons in the outer shell. Remember, that makes a total of 6. Well, if each of those atoms shares their outer electron with another atom, then we end up with 8 in the outer shell of the carbon atom. And again, that is very stable. So this is a good example of sharing bonds. An ionic bond is a bit weaker, and when atoms lose or gain electrons, they form ions. And if you have a positive ion and a negative ion, they actually attract each other and form a compound. Examples include salt. The mineral name for salt is halite, and you might be familiar with the chemical formula, sodium chloride. So let's take a look at this. What element number is sodium? It's number 11. So it must have 11 protons, and if it's neutral, it also has 11 electrons. What about chlorine? Well, chlorine's over here. It's number 17, so it has 17 protons and 17 electrons. So here's a little cartoon of these 2 atoms. Here's sodium, and remember it has 11 protons and 11 electrons. So the first 2 electrons go in the inner shell, then we have 8, and then the 11th electron is all by itself in the outer shell, which is only loosely held. Chlorine has 17 protons and 17 electrons. So we have 2 in the inner shell, then 8 in the next shell, that makes 10, and then the other 7 are in this outermost shell. And as I mentioned, when the outer shells are filled, they're very stable. So chlorine would really like to have this electron from sodium to give it a complete shell. And that's exactly what happens. The electron is transferred from sodium to chlorine, and as a result, sodium now has 1 missing electron compared to its number of protons, so it actually has a positive charge. It has 11 protons and 10 electrons. And this is how we write that. Sodium plus 1. Chlorine has an extra negative charge, so the 17 protons are matching with 18 electrons, and it gives it a net -1 charge, and we write it like that. These are ions, atoms that have a charge. Now it turns out that sodium and chloride ions form a cubic structure. And here I have a piece of halite or salt, sodium chloride, and you can see that it is a cubic structure, how it breaks and how it forms. And if you look at the salt at your house, at the table, shake some on your hand and look at it real closely, you'll see that it's little cubes. So this is a cubic structure, and it keeps repeating itself until eventually you get a large enough crystal that you can see. So the crystal shape is directly related to the arrangement of the atoms. And here's a nice picture of some salt, some halite, a little bit clearer than the one I just showed you. You're now going to move on to Inside Minerals, a video from the City College of San Francisco. It's going to go over the definition of a mineral. It'll introduce you to mineral families. It'll present some important mineral properties such as cleavage and fracture, and it will explain how some minerals form from cooling magma.